So I'm going to start off asking you a simple question. What do Novak Djokovic and Maria Sharapova share in common? Go ahead. They do. In fact, they've both been world champions at tennis. But they share something else, because I'm going to talk about graphene. Who knows what graphene is? Go ahead.
It's a one atom of graphite, and it's the strongest material, I think, now.
That's correct.
It's two-dimensional, and it has the potential to be like smooth, flexible string.
That's great. Now, I'm going to see, does anybody know how graphene was discovered? Go ahead.
Well, don't you make it with like a piece of tape and like graphite, and you just like take it off and then you dissolve the tape?
Sounds good. Boy, you don't need me. I think you just need each other to have a discussion on this. So if I were to pull out a block of graphite, here's what graphite looks like as it comes out of the ground. It's a block of graphite. Anybody know what you can do with graphite if I pass it around, besides peel it with Scotch tape? You can write with it, yes. So a pencil is just a combination of graphite and clay. Now with any luck, I do have Scotch tape. So here's Scotch tape, and here's graphite. In 2004, Novoselic and Geim had this idea, they're two physicists, that if you could peel down to a single layer, you could study it. And 6 years later, they won the Nobel Prize in Physics for the, quote, discovery of graphene. Although I'll show you one of the things I like about UCLA. It's a great place. So 4 years earlier, one of my colleagues from engineering, Tom Hahn, came to see me, and he had this idea that he needed a single layer of carbon to reinforce polymers. And he asked me if I could do it because he had heard that I work on carbon. So I told him I probably could, and so he encouraged me to do this. And so I actually have a patent from 2002, 2 years before graphene was discovered, on how to make it. But let's get back to Maria Sharapova and Novak Djokovic. So they both happen to use tennis rackets made out of graphene. Now, I don't play tennis, but what I do play is squash, or maybe I should say I used to play squash, because you wonder why I'm on this cart. So I was in the middle of a squash match. I've been playing 4 times a week for 30 years. And an hour into a match that I was actually winning, I went back to put away a shot. Squash is played in a small court, by the way, if you don't know. It's the world's most intense sport. I can say that because my wife handed me an article about how it burns the most calories per unit of time of any sport. And number 2 is kickboxing, and I won't get near that. But anyway, so you're in a small room. You force your opponent to the front. He hits it back, so I went back to hit the shot, and my Achilles tendon snapped. So hence, I'm in a cast. But I'll get better and get back to this. But anyway, here's my old racket. And one of the shots is, if your opponent's good, they put it in the back corner, and you have to push your racket against the wall to dig out the ball. So I did that, and when I did that, my racket snapped. This was before my Achilles tendon snapped. So this is actually quite interesting. I'm going to pass around my old racket, and what you'll see is it's hollow, okay? And it has carbon fiber in it. And carbon fiber is incredibly strong, although it does break. So take a look at this, and you'll see what a modern tennis racket, or in this case, squash racket, looks like. Same if you play golf. Golf clubs look like that too. So that's my old racket. Guess what my new racket's made out of? Sounds good. Here. Can you read what it says right there?
Graphene.
So it does say graphene. So it says graphene right on it. I'll pass this around, and you can take a look. Now, you may say, where does the graphene go, and what does it do? So I need to tell you another story. So back around the same time that I got started working on graphene, there was something called carbon nanotubes. Has anybody heard of a carbon nanotube? Oh, you have. What's a carbon nanotube? Any idea? Oh, wow. That's impressive. I'm glad I don't have to do that anymore. But, okay, so let's talk about what a carbon nanotube is. So imagine a sheet of carbon, and you rolled it up and made a roll. Okay, that would be a carbon nanotube, especially if it was hollow. So just a cylinder. Okay, so in the 1990s, carbon nanotubes were discovered, and in the 2000s, people were using them for applications. And one of the first applications was to reinforce tennis rackets. So I was in UCLA has some really professional tennis players. I mean, they're playing college, but they'll go on to a pro career. And there's a very good tennis store in Westwood, not very far from here, a few blocks from here, that also sells squash equipment. So I was in there one day, and I went over to the owner because they weren't very busy, and I said, I couldn't help but notice that you're selling the new carbon-reinforced tennis racket, and I'm just curious if it works. And he said, oh, let me show you. And he goes in the back room, and he gets an oversized demo racket. And he said, you know, all the stress in the racket is right here, right? You hit the ball here, stress is on the neck. And he said, this is where they reinforce with graphene. So, and then he pulls this demo racket apart, and he shows me, here's the carbon fibers, and that's where they have the carbon nanotubes. He said, whether it works or not, I don't know. You're the scientist. You might know. But I'll tell you one thing. It sells tennis rackets. So you can decide for yourself whether graphene does anything. Any questions before I get started? Okay, if you have them, let me know. I'm going to give you a little bit of an introduction. I may have called up a little bit too detailed of a lecture, so I may skip some slides. But we're going to talk about the synthesis and applications of graphene. So how do you get there? What do you do with it? So here's a nice slide to start with. And if you look at this, the top layer is a single layer of graphite. Okay, and that is graphene. And if you look to the left, who knows what this is? This could be on your SAT test. No, who knows what that is? Go ahead. Fullerene, good. In fact, this one's called C60 or Buckminster fullerene. Who is Buckminster Fuller? That dude, yeah. Actually, if you want to know who the real dude is, there's a movie like that, Jeff Bridges, and I'll digress. You guys know who Jeff Bridges is? He won an Academy Award. So one of my favorite stories is in Young Hall, in chemistry. He stops me one day and he says, Rick, I like your shirt. Can I take your picture? It's a true story. So he takes my picture. I get home. My wife's like, I picked out that shirt. I should get a credit. Well, it turned out he played a homicidal maniac chemistry professor. Yeah. Oh, and you're probably wondering how he knew to stop and take my picture. Yes. So he called up the chair of my department the week before, and he said, I'm a character actor, so I'd like to meet some of your faculty. So the chair said, we'll start with a party on Saturday night. So I met him at a party Saturday night. Monday morning, he sees me in the hall. That's it. So, yeah. Anyway.
LA for you.
Yep. And so in the famous movie, The Big Lebowski, he played the dude. So when you say the dude, it actually means something. All right, anyway. So Buckminster Fuller was a inventor. He was a futurist, but he's famous for coming up with a geodesic dome and expounding on its properties. And so when we came up with a carbon that looks like a geodesic dome or close, it was named fullerenes or Buckminster fullerene in this case. And how do you get there? Well, if you take graphene and you put in 12 5-membered rings, it closes on itself, and that's C60. Okay, on the other hand, if you take graphene and you roll it up, you get a carbon nanotube. So there's a carbon nanotube. That was the first thing that was used to reinforce tennis rackets. And finally, if you stack graphene up, you get graphite. And graphite is the block of material that's going around. What's interesting is, of course, graphene was the last to be discovered. Graphite was discovered in the Middle Ages. Carbon nanotubes were discovered, actually fullerenes were discovered in the 1990s. No, 1985, this in the 1990s, and this in the 2000s. Okay. Just out of curiosity, anybody know what the first use of materials almost invariably is? What would you use a new material for? It's not a pleasant thing to think about because science cuts both ways. You can use it for good or evil. Yes. Weapons, yes. Yeah, almost invariably anything new that's discovered, if there's a military use, the military will use it because they can afford to pay for it, especially. So graphite was discovered in England in the Middle Ages. Its first use was kept secret. Its first use was they found if they rubbed it on the inside of cannons, the cannonballs fired further. So there you go. We did that before we did pencils. Okay, So now you know that graphene, although the last to be discovered, is a building block of all other forms of carbon. Or you can think of it that way. I like to think of it that way.
Wait, can we go back for a
Absolutely.
second and follow that route?
Yes.
So what was the first military use of the other carbon?
Oh, that's even a better question. So carbon-60, despite all its interest, has never actually found a real application. Okay, now,
Okay, for Becky.
I'll give you a few things that it can do. So it turns out it prevents HIV transmission. So sounds great, right? Except you'd have to give so much to a patient, it would do them harm. So it physically blocks it. So that is not realistic. Carbon nanotubes, I told you they put them in tennis rackets. Whether they work or not is another thing. But it's not known yet whether they're completely safe. So you can buy all these things. They're sold on the market, but they're usually used for research rather than for anything. But
So the carbon tubes have not been used in any war, as far as
as far as I know, a lot of these things can be used to carry drugs, and if you can carry drugs, you can carry nasty things. So we don't know exactly what they're doing with them because there's always that possibility. So I don't know. I just, when you think of science, we like to think of the good things, but it depends who's using it. Yes? Excellent question. So let's think about how a pencil works. A pencil is graphite and clay, and the layers slide over each other. So when you hit the paper, the layers slide over. And the reason they do is if you look at this structure, the carbon bonds in the plane are very strong. They're actually stronger than in diamond. Diamond has single bonds. Here the bonds are 1 1/3. But between the layers, the only thing holding them together is something called Vander Waals bonds. Have you guys heard of Vander Waals bonds? Dipole-induced dipole. Very weak forces, on the order of 1 kcal per mole. A chemical bond is about 60 kcals per mole. So 1 kcal is very little. So these can slide very easily. So if you line a cannon with them, the cannonball will literally, instead of having friction, will just take some layers with it. So that's why it lowers the friction, basically. So if your doorknob sticks, you can go to the hardware store and you can buy graphite mixed in with oil. And you can put that in your doorknob and it works quite well. If you spend a little more money, you'll get molybdenum disulfide, which actually has a lower coefficient of friction. And there's engine oils that you can put in your engine. And then instead of metal parts wearing against each other, the layered compounds coat them, and the layered compounds wear against each other and just kind of peel off. Yeah, please ask lots of questions because then we'll get to the heart of the matter. Anybody else here? Yeah, so I don't know, I mentioned the military uses, but you're right, I don't know for sure what carbon nanotubes. The other thing that's interesting about buckyballs, they work really well in organic solar cells, but none of them have been commercialized yet. So, yeah. Okay, I'll give you a little bit of history. I'm going to tell you about our work on interpolation exfoliation. And I mentioned Vaslav and Guy mechanical exfoliation, but there's other ways to make graphene. You can take silicon carbide, which is a very high temperature material, and if you heat it up, the silicon will leave and you'll end up with a layer of carbon, but it's on a surface, so it's hard to use. And if you want to do electronics, you use something called chemical vapor deposition, where you grow carbon on copper, and then you have to etch the copper away. Okay. This is a block of graphite, and this is one of my favorite pictures. This goes back to before I got to UCLA, which was a long time ago. I was at our sister school up north, and I was working with Neil Bartlett. This is from his lab. This is a block of graphite the size of your thumb. And we're hitting it with a laser right here. Now, a normal material would heat up in 3 dimensions. But of course, graphite is not a normal material. And heat travels by 2 things. One is phonons. Has anybody ever heard of phonons? Heard of it. Does anybody know what it means? Anybody know what photons mean? Good. What's a photon? Light. So it's a quantum of light. So a phonon is a quantum of vibration. It's vibrational energy. Okay? So, yeah. So heat travels by, it's a cool term, right? Heat travels by phonons, lattice vibrations. And so if you think of the structure, instead of picturing this, picture that structure of graphite. All the bonds are in plane, so all the lattice vibrations are in plane. So if you hit here, the heat travels this way. Now, heat also travels by conduction electrons. It turns out the conduction electrons all travel in that direction. So we hit the laser here. If you touch here, you burn yourself. If you touch the top, it's cold. And this is the only picture I've ever seen of a molecular scale property in real 3 dimensions. Okay, and I've shown this picture all over the world, and no one has ever come to me and said, oh, we've got this other picture. So this is it. If you want to see something that happens on the molecular scale that you can actually picture with your eyes, there it is.
What kind of microscope did you use for that?
It's called a camera. So I don't mean to be facetious.
No.
No microscope. This thing is the size of your thumb. This is just a camera. And this was taken in the 1980s. So we're talking not a good camera. I mean, your cell phone is much better than any camera that existed then. Yeah. Yeah, I've also been asked a really interesting question. Do you notice that this thing where it gets hot is curving in? Yeah, so you'll be interested in this from an artistic point of view. Graphite and graphene are very unusual. They have a negative coefficient of thermal expansion. What does that mean? What does that mean if you heat up something with a negative coefficient of thermal expansion? Please. That's correct. So in theory, if you heated this up, the part you heated up would shrink, which is extremely unusual. Okay? However, we did the calculation, and that shrinkage is too much. You actually couldn't see it. So this is just a photographic illusion. But it is true that it has a negative coefficient of thermal expansion. So that's kind of nice.
Even though it's an illusion, it's true.
Yeah, that's correct. That's correct. Yeah. Yeah, my favorite, I collect things that I call scientific urban legends. Yeah, and my favorite one is, do you know if you go to a cathedral in Europe, you'll see that the glass, the stained glass, is thicker at the bottom and thinner at the top. Anybody know why that is? Say again? That's true. Yes, this is a good crowd. So, yeah, I'm impressed because when I grew up, I learned that glass is a liquid, and therefore, if you looked at something from the Middle Ages, it'd be thicker at the bottom and thinner at the top because glass is a liquid, so it flows. Not true. The time constant for glass to flow is about 10,000 years. That cathedral's been there for 500 years. It's when glass was made in the Middle Ages, they didn't know how to make flat glass. So it was all irregular. So if you were installing the glass, which would you put down, the thick part or the thin part? So you put down the thick part, and somebody comes 500 years later and said, oh, glass is a liquid, and look what happened. Anyway, let me go on. So this is what we did. Knowing that graphite is a layered compound, we knew we could do interpolation chemistry. We just heat it with potassium. You've got to do this. It's air sensitive, so you do this in the absence of air. But we made what's called a first stage interpolation compound. So for every layer of carbon, there's a layer of potassium plus. We also know that this is incredibly reactive, so we just hit it with alcohol or water and blow the layers apart. And after we did that, this is a transmission electron microscope picture. And this is what we created. It's called a carbon nanoscroll. It's just carbon rolled up. And you can see how thin it is. You can see the carbon grid. This is called the carbon grid that you use to take the image. You can see it right through the thing. And here's a more tightly wound scroll, and here's a whole lot of scrolls. Now, our goal was to make graphene. And you'll see that we published this in 2003, the year before Vander and Geim did their work on to make graphene. And here's our patent from 2002. So I actually got to, I showed this last year in a conference in Barcelona after Vander and Geim, after Andre Geim spoke. And he said, Rick, we need to go out for a drink. And he said, you know, I quoted your work a couple times in our Nobel Prize address. And I'm like, I do know. And I said, and if it wasn't for you, no one would care about what we've done. So anyway, they earned the Nobel Prize in physics. They studied all the physics of it. But discovery is a different question. Okay, after Novoselic and Geim did their work, I realized if graphene is ever going to be useful, we're going to have to not make pieces of it. We're going to have to make tons of it. And peeling graphite, mechanical exfoliation is never going to work. So I switched my line of research to chemistry, to liquid processing. And it turns out that there's a material called graphite oxide. It's really graphene where it's all oxidized. There's a carboxylic acid, there's hydroxyl groups, there's epoxide rings. And the neat thing is once you oxidize the edges, it disperses in water. And this has been known for a long time. Here's a paper from 1860. Would anybody guess that chemistry goes back over 150 years? Kind of surprising, right? But scientific papers were written back in the 1800s. So in the 1800s, they knew you could oxidize graphite and put it in water. What they didn't know till the last 10 years is this material is in water as single sheets. So the question then is, it doesn't conduct electricity. Can you get rid of these oxygen groups and get back to graphene? Because if you could, this is completely scalable and very cheaply. And so this is what we've been focusing on for the past decade. We've taken this graphite oxide and we can make graphene paper out of it. We can make field effect transistors in electronics. We can make sensors. We can make graphite oxide foam. We can do lithography, and we can make supercapacitors. And I'm going to tell you a little bit about this. How much time do you probably? Okay. So first, I'm going to tell you a little bit more about graphene oxide. So the first thing we did as chemists, we hit it with hydrazine, which is a good reducing agent, N2H2. And when we did that, this is the reduced form. It still disperses in water and shows what's called the Tyndall Effect. So the Tyndall Effect is, if this were a solution, a laser would go right through it. But you'll notice the laser is being scattered. It's being scattered because you have individual sheets of this chemically reduced graphene oxide. So we have graphene sheets. And you may wonder, why do the graphene sheets stay in solution? Well, they stay in solution because every graphene sheet has a negative charge. And they're so negatively charged that they repel each other. How do we know that? Well, they show the salt effect. If you throw in sodium chloride, it neutralizes the charge, and they flocculate out. They just drop out, right? Because now they have no charge. And if you look at this is atomic force microscope picture. And this is the graphene we made. You see all these flakes. And if we run a probe along it, they're about 1 nanometer in height. They're very thin. So people have decided these are individual layered flakes. And so this was a paper we published 10 years ago in Nature Nanotechnology. And a few years after we published it, they contacted me and they said, congratulations, editor-in-chief, you have the most highly cited paper in the history of our journal. So a normal paper gets about 20 to 30 citations in its lifetime. If you have a really good paper, you get 100 citations. This paper has over 7,000 citations. Yeah, so you can see how popular this area is. Again, if you have questions, just stop me. Okay, now, because that's scalable, we can make as much as we want. So we make a beaker full of it, we run it through filter paper, and we trap all the layers of graphene. And we do that, we can peel it off the filter paper. So this is pure graphene paper. And you can see how flexible it is, and you can see your reflection here. This is a paper we published in Science about 10 years ago. Now, you may say, well, wait a second, isn't that graphite? Because it's just layers of carbon. No. Graphite's three-dimensionally ordered. It has an AB-AB stacking. This is just random arrangements. But it's similar. It's just pure carbon. You can have some fun. We combine this with carbon nanotubes, and we showed in hydrazine, N2H2, it's completely stable. So you can make these solutions, or dispersions technically, and keep them around. Now I have a colleague in engineering, Yang Yang. He's famous for a number of things, including organic solar cells. And so he said, what if we try to make a flexible base for a solar cell? So right now, if you take your cell phone, you know that you have a clear window, but it's electrically conductive. How do you do that? It uses indium tin oxide. And you may wonder, what would happen if I bent my cell phone? Has anybody tried that? Yeah, not a good outcome, right? You'll crack the screen. But in a few years, in fact, there's some existing, you can get flexible cell phones. And that depends on having a flexible, transparent conductor. So here's indium tin oxide. This is a current voltage curve. And what I'm showing here is we put some of our graphene with carbon nanotubes onto plastic. PET is polyethylene terephthalate. That's what your Coke bottle or water bottle is made out of. And here's indium tin oxide. That's what's used on your cell phone. And then we put it on plastic and we bent each of them 10 times. And when we did that, you'll notice that the indium tin oxide drops by 3 orders of magnitude in conductivity. But the graphene carbon nanotube combination doesn't have any change. So basically, we have a flexible, transparent conductor. And so one of the reasons you'll have flexible electronics and flexible cell phones is because you can use a layer or 2 or 3 of graphene, and it'll conduct and be relatively transparent. Okay, what else can you do? You can make sensors. So this is 2,4-dinitrotoluene we're detecting with our graphene sensor at 52 parts per billion. Now, you may say, I don't care about 2,4-dinitrotoluene, but I think you probably would if you know that its cousin is TNT, trinitrotoluene. And whenever you have TNT, this is the volatile part. There's always some of this. And the vapor pressure is about 700 parts per billion. So we can detect this with pretty good signal to noise. So you could use graphene to detect. So you can decide whether that is a good application or it could be a military application. How about that? All right. Now for some fun. This is graphene oxide that we freeze dried. So this isn't, it's not a conductor, so this golden brown thing. And I'm just going to light it on fire. And now the question is, do we have sound? And so we're going to find out. Okay, so oh, we have lots of sound. Okay, now it looks like it burned up. I don't know if any of you have ever played with snakes on the 4th of July, but it actually doesn't burn up. It's still there, and what's left is pretty much pure carbon, kind of an uncontrolled reaction. But now let's try that with graphene oxide paper and a flash of light from a camera. Yeah, so that was graphene oxide paper. We hit it with a flash. It absorbs the light, it gets hot, and blows off carbon dioxide. And that's 2 uncontrolled reactions, but imagine controlling this. And we can control this by using something called LightScribe. What is LightScribe? It's a $25 device. You put it in your computer stack, and it consists of a 780 nanometer laser and a magnifying glass, plus a computer program that can raster any image you want. So we simply do this, and this is, again, a current voltage curve, and this just shows that the graphene oxide, the golden stuff, is insulating. And as soon as we hit it with a laser, we convert it to graphene, it becomes conductive. Okay, now, as I said, you can make any pattern you want. So here's, on plastic, we have the graphene oxide, the insulating orange-brown stuff, and we make all sorts of interesting patterns. So this one's for you. We paid an artist for a picture of a person with a computer for a brain. And we reproduced it in laser-scribed graphene. So if you look at this, the light part is graphene oxide. The dark part we've turned into graphene. And this, using grayscale, is somewhere in between. So this is the conducting part, that's the insulating part. But you can see that the reproduction is pretty decent. Okay, so that's art. Now let's talk about science. So we can take an ordinary CD disc, we put a piece of plastic, we coat it with graphene oxide, we tell the laser to darken the whole thing, we cut it into strips, we put a separator between it, and we make what looks like a battery, but it's really a supercapacitor, because it will store all its charge on these surfaces. So what I'm going to show you is it's completely flexible, and this is called a cyclic voltammetry curve. Current versus potential. Now, when we run it, you see you get this rectangular thing. That means all the charge is capacitance. It's just charging the surface and then discharging the surface. And what we're doing is we're plotting this as a function of bending angle. And you'll notice that every curve falls on each other. So it doesn't matter. This is totally flexible. Imagine trying to do this with a battery, right? If you tried to do this with a battery, it just crack. But our stuff, it doesn't matter. You can run this electronically while doing that. Now to prove it, we made a little movie. And so I will play this for you, and you'll see that we can use this to light electronic devices.
Started.
So what we have is a graphene supercapacitor that we charge up. It's running this LED, and now we're bending it back and forth just to show you that the LED is unaffected. You know, it doesn't matter how much you bend it. And for good measure, we put a piece of graphene in line as a conductor. So you can use this to store energy. You can use it as an electronic conductor. There's all sorts of things you can do with it. Now, how are we going to store enough energy to, let's say, run your computer? Well, your computer runs, if you look at the back, at about 14.4 volts and about 4,400 milliamp hours. If we're using an aqueous cell, it only puts out 1 volt. If we use a non-aqueous cell, we can get up to about 3 volts. Or ionic liquid, we can get about 4 volts. But it doesn't matter. Let's just say we use a 1-volt aqueous cell. So here's potential versus time. There's 1 volt. If we put 4 of these in series, notice that we go from 1 volt to 4 volts. If we put 2 in series and 2 in parallel, we go from 1 volt to 2 volts. Notice that the area under the curve doubles. And so essentially by putting them in series, we up the voltage, putting them in parallel, we up the current. So you can put as many as you want, and so you can run any device that you want. Now, how stable are these? Well, here's the cycle life. So we ran 10,000 cycles, and you'll see the capacitance retention is quite good, very little loss. You can wonder about the shelf life. Here we ran it for 4 months, and it has really good shelf life. So here's a Ragone plot. That's power density in watts per kilogram versus energy density in watt-hours per kilogram. Now, here are commercial supercapacitors. It turns out that supercapacitors are already a billion-dollar business. It's a company in San Diego, Maxwell Technologies, that sells about 20% of the world's supply of supercapacitors. They're used for backup power for trucks. They're used for backup power for cities. They're used for all sorts of things. But they don't really encroach on lithium-ion batteries, which are much more energy dense. However, these new ones that we made, here are the solid-state ones, here are organic ones and ionic liquid ones. And so we're already storing as much energy as lead-acid batteries, and we're starting to approach that of lithium-ion batteries. And this is just another way of making them. Here's more structures. And I want to talk just briefly about a couple other possibilities. So one is that we can stuff battery material in and approach the energy density of lithium-ion batteries. But another thing that I'm fascinated about is little tiny electronic devices. Here's pacemakers, hearing aids, radio frequency devices. Here are lithium-ion batteries that are tried to miniaturize. Turns out they don't miniaturize very well, but the things we're doing miniaturize very well. I can show you that because we can run a laser and we can create over 100 electronic devices, these interdigitated devices, on a single pass. And there we go. And we can make these into supercapacitors, and those supercapacitors are as good as the lithium-ion batteries. Okay, what I'm going to do now is I want to show you a movie that was made for the PBS program Nova. But if anybody's more interested, we wrote a review not too long ago in Nature Review Materials called Graphene for Batteries, Supercapacitors, and Beyond. Or if you look up my name, you can find lots of things on the internet. But let me show you this video, because I think this captures what we're trying to do best.
There's a lot of talk about renewable energy, but how feasible is it? A major barrier, believe it or not, is battery storage, and that's where something called supercapacitors come in. They run on static electricity, and they're capable of recharging and delivering power faster than batteries, but they don't store as much energy, yet. Enter chemist Rick Kainer. You see, supercapacitors are limited by the surface area available for holding electrons, and Kainer's developed a technique to produce electrodes with lots of surface area out of graphite.
This is what graphite looks like as it comes out of the ground. It's a mineral.
And this is what's in a pencil?
Absolutely. So a pencil is nothing more than graphite combined with clay. So this is the material that's used in essentially all batteries as at least one of the electrodes. So the question is whether you could make this in a high surface area form. And that is where graphene comes in.
Graphene is the strongest material ever tested. It's a layer of carbon that's 1 atom thick, giving it extremely high surface area. Kainer says 1 gram of the stuff would cover 4 football fields.
Graphene provides the high surface area and conductivity necessary to store large amounts of charge.
Which means graphene might just allow supercapacitors to be even more super. And Kaner's lab has come up with a surprising way to make it. It starts with plain old graphite. This is a chunk of graphite oxide that was mixed with water and then freeze-dried. Maher El-Kadi hits it with an ordinary camera flash.
Big flash.
Yeah, it's just a little big. So just watch what's going to happen.
Okay. Oh,
The pulse of light's converted to heat, burning away the oxygen and leaving behind graphene.
that's graphene right there?
So what's left over, we call it now graphene foam.
Kaner's lab has developed a system to print exact designs. A layer of plastic gets coated onto the surface of a CD with a solution of graphite oxide. Once dry, it's inserted into a CD laser labeler.
Oh, that's wild that you put it up.
But instead of doing its usual job of etching a label, wherever the laser hits the dried graphite oxide, that spot's transformed into graphene.
Oh, I like this technology.
Aside from a graphene likeness of David Pogue, El-Kadi's printed 2 graphene electrodes.
Obviously, there's a huge worldwide market for CDs with pictures of me in graphene, but I'm guessing that these are more important to the future of mankind. You've etched circuits out of the graphene?
Yeah, so these circuits are basically micro supercapacitors. And this stores as much charge as these like very bulky capacitors that you will find in any electronic device.
You mean this totally flat pattern right now
Yes.
could hold as much charge as this capacitor?
Yes, and we actually made them store 1,000 times more charge as this size of a capacitor.
If we could scale this to the size of electric vehicles, then you could actually, instead of pulling into a gas station, you'd pull into a charging station, and within minutes, your car would be ready to go.
An electric car that you can charge as quickly as it would take to fill up?
I would definitely like to see that happen, and that's exactly what we're working on.